Hello and welcome. Today, we're going to break down a really clever cryptographic structure called AMBS, which was created by LAEV. It's a concept that completely rethinks how we can use public blockchains like Bitcoin, not as some clunky database, but as a perfect, incorruptible public witness. All right, let's dive right in. And this question right here, this is the heart of the matter. We all know Bitcoin is amazing for creating a permanent, unchangeable record. But, the moment you try to stuff too much information directly onto it, the whole network just slams on the brakes and the costs go through the roof. This is the big engineering puzzle that AMBS was built to solve. So that challenge leads us to what you could call the blockchain data dilemma. It turns out there are these fundamental tensions, this kind of push and pull, that happens anytime you try to anchor real-world data onto a system like Bitcoin. And we can actually break this problem down into 4 key pressure points. First up, on-chain overload. Look, it's just way too expensive and slow to put lots of data on-chain. Second, you've got this tension between verifiability and replication. You want anyone to be able to verify your data, but they shouldn't have to download the entire dataset, the whole shebang, just to do it. Third, and this one's a bit more subtle, is semantic ambiguity. The same final hash could potentially be created from different data structures, which just creates confusion. And finally, there's operational compatibility. Real-world systems need to crank out proofs frequently and in a standardized way. The solution to all of this required a really fundamental shift in thinking. It turns out it's not about what data you put on the blockchain, it's about what you commit to on the blockchain. And this is the core insight from LAEV right here. The real power isn't in publishing your data for the world to see. No, the power's in publishing an unbreakable cryptographic promise, a commitment about that data. The blockchain's job is simply to act as a witness to that promise, not to hold the data itself. So let's be crystal clear on this. We're not using Bitcoin like some giant, slow hard drive. We're using it as a public notary, a witness that can certify that a specific piece of data existed in a specific state at a specific time, and that proof is then sealed forever. And this brings us right to the solution they engineered, the AMBS. So what is this thing exactly? The AMBS is a special kind of data structure that's laser-focused on one purpose, creating a single, tiny piece of information, that commitment, that you can anchor onto Bitcoin. This little commitment is incredibly cheap and efficient to store, but it packs within it the verifiable and completely unambiguous proof of a much, much larger set of data. Okay, so how does it work its magic? Well, the secret sauce in the AMBS is a concept we can call the binary switch. This is the key innovation that makes it fundamentally different from a regular old Merkle tree. Think about a standard Merkle tree for a second. It just mashes pairs of data hashes together using the same hash function over and over again until you get one single root hash. Simple enough. But here's where the AMBS flips the script. It introduces a choice. At every single step, it uses one of 2 different mathematical functions. We can just call them F0 and F1. So what decides which one to use? Well, that's where the control vector comes in. Imagine this binary control vector as a set of instructions, or even better, a recipe. It's just a simple string of zeros and ones. But this string dictates exactly how the Merkle tree has to be built. So you're not just committing to your data anymore, you're also committing to the exact process of building the proof itself. And the process is just beautifully simple. You take 2 nodes you need to combine. You look at the next bit in your recipe, that control vector. Is it a 0? Okay. You use function F0. Is it a 1? You use function F1. You just repeat this process all the way up the tree. What this does is it makes the final root hash dependent not just on the original data, but on the unique path dictated by that string of zeros and ones. This whole mechanism brings us to the core principle of the AMBS, that one tiny piece of data you anchor on Bitcoin becomes the absolute ultimate source of truth. And this is where the real power kicks in. Once you've anchored that commitment, you've essentially set the rules of the game in stone. Any attempt in the future to prove something about that original data must follow the exact same recipe. There's no wiggle room, no space for interpretation or ambiguity. The anchor governs everything. So this on-chain commitment we keep talking about, what is it really? It's the only thing you ever have to publish. It's one final hash. But here's the key. It's not just a hash of the data. It's a hash that cryptographically binds the data's root and the rules used to create it, all rolled into one inseparable package. Now, if we pop the hood on this commitment, we can see it has a few parts. You've got the committed root, which is the final output of the tree. But crucially, it also includes things like a scheme ID, so everyone knows which version of AMBS you're using, and a policy ID to define the exact formatting rules. This just prevents any future confusion. And most importantly, you have the parameters hash, which is a commitment to that binary control vector. You've literally frozen the recipe itself into the proof. Okay, this is all super interesting from a technical point of view, but why does it matter in the real world? Let's take a look at the impact. What you get from this architecture are some seriously powerful properties. First, it's cryptographically compact. That means the on-chain footprint is tiny, so it's cheap to anchor things frequently. It also allows for independent verifiability. Anyone can check your work without having to trust you. It completely eliminates ambiguity, because remember, the rules are baked right into the commitment. And all of this means it has massive operational scalability for systems that generate tons of data. And here's a really key takeaway. Think about the mismatch in speed. Real-world systems can generate thousands of events every minute. The Bitcoin blockchain confirms a new block maybe every 10 minutes. AMBS acts as this perfect bridge, allowing you to batch all those high-frequency events into a single low-cost transaction without ever losing the verifiability of each and every one of those individual events. And hey, this isn't just some cool idea on a whiteboard. AMBS is designed to be the backbone of real working systems. The Hash Paper Pool Service, or HPPS, uses it for documentary evidence. The Universal Consensus Time, or TUC, uses it to create a verifiable timeline of events. And eBitcoin uses it as a fundamental evidence layer. These applications absolutely depend on the efficiency and the rock-solid integrity that AMBS provides. So, to wrap this all up, AMBS really transforms the blockchain from a slow, clunky database into a high-speed, immutable public witness. It lets us create undeniable proofs of real-world happenings with incredible efficiency. Which leaves us with one final thought to chew on. If the anchor on the blockchain is a witness, what truths can we now choose to freeze in time forever?